Hello, welcome to the VaNTAGE seminar. This spring, we're continuing our series of talks on machine learning explorations in number theory. And today, we're very happy to have Coco Huang, who will be talking about from explicit algorithm extraction to sparse search, machine learning for constructive mathematics. And Coco, is it all right if we record this talk?
Sounds good. Thank you.
Great. And we'll keep most of the questions to the end, please. All right, Coco, please go ahead.
Thank you very much. First, I would like to thank the organizers, Drew and Rachel, for inviting me. It's truly an honor to be here. Today, I want to talk about machine learning for constructive mathematics. So recently, there are a lot of talks and a lot of research on using AI to formalize mathematics and prove theorems. They could come at a computational level. For example, IMO, Putnam, there are a lot of great provers currently, and they're keeping improving. And on the other hand, there are actually a lot of progress on the research level of things as well. For example, first proof as a benchmark for large language models. And on the proving side, there are AI-assisted proofs as well as maybe I would say like semi-autonomous proofs in number theory and algebraic geometry. But today, I will take a different perspective. I want to focus on several ways that machine learning can contribute to constructive mathematics, an area I also think is very important too. In particular, I want to give two case studies. The first one is finding explicit relationships between mathematical structures. So this you might find this kind of interesting because machine learning models are known to describe relationships rather well, but a lot of times they're being regarded as black boxes. So today we want to show that the black box can be opened and you can really get a explicit handwritten relationship between mathematical structures. And on the parallel direction, we can also use machine learning to find sparse examples or counterexamples related to open conjectures. And along these two parallel directions, maybe as a byproduct, sometimes we might have interesting observations that could possibly be formulated as conjectures. So let's start with a number theory example. For an elliptic curve over the rationals, for this cubic equation, we all know that we can associate an L function defined as a product of local Euler factors, the LPs. And for a very nice thing is that for all but finally many p's, the curve E, elliptic curve, if it has a good reduction at the prime p, then the Euler factor, the local Euler factor, is almost exclusively explicit, except for one number, which is AP here. The AP is the Frobenius trace. And in the case that if P is a good prime for the elliptic curve, then this AP is explicitly P plus 1 minus the number of solutions of elliptic curve at the finite field. So in some way that this number AP, the Frobenius trace, encodes the information of the elliptic curve at the prime P. The first result I want to demonstrate was a results on learning Euler factors. And this was carried out during mathematics and machine learning program at Harvard CMSA. And this is a joint work with Babe, Chaton, Costa, Lee, Lori Duda, Narayana, and Pozniakov, my wonderful collaborators. And in this project, we asked a very concrete question, which is, given the AP values, these Frobenius traces of an elliptic curve, can a machine learning model predict the other AP values? And in some way, this is asking that, given the local information of an elliptic curve at some primes, can you use this information to predict the local information at other primes? I should say that I think, to the best of our knowledge, I don't think there is an algorithm that describes this very nicely. The model the machine learning model we use include neural networks as well as transformers. So the transformers unfortunately, we have to go a little bit into it, but it's implemented using end-to-end. That is a sequence-to-sequence transformer for short integer sequences. So they're not designed for languages. They're really designed for integers. And the data we use, we call them ECQ6. And in most experiments, we use 2 million curves for training, and we use 10,000 curves for testing with no overlap between them. So the idea is that we take a subset so the model can learn the behavior of AP values, and we take a non-overlapped small data set subset so that the model is not cheating and try to generalize the behavior that it learned during training. And importantly, we only keep one curve for each isogeny class because AP values are only depending on the isogeny class. Let's go straight to the point. We ran many experiments, and I want to show you some of the results that we found. The first experiments that we ran was to predict the value of A97. And specifically, what was happening is that we take all the primes less than 97. So that's 24 of them, A2, A3, all the way to A89. And then we want to use these values to predict A97. So I should make a note that A97 is between -19 and 19. So this is quite a lot of values. And the results is that the prediction accuracy, so how many times the model gets the prediction of A97 correctly, is about 50% of the time. So that is definitely not a very impressive number compared to you see a lot of machine learning results, 100%, 98%, and so on. But if we compare the baseline accuracy from random guessing, that's about 2.5% of the time we should get this correct. But however, this wouldn't be a very interesting talk if this is nothing. If this is telling us nothing about number theory. So if we take a closer look of what the model does, is that the main difficulty of the model is that the model struggles to predict the sign of A97. So if we look at the figure here, there is two lines that are very significant. So there is the most significant line, that is the 45-degree line. So that means that the value of the model is predicting the value perfectly. So the true value is equal to the predicted value. So true value is on x-axis and predicted value is on y-axis. Apart from that, there's also another very significant line that is negative 45-degree line. So that line would mean that the model is predicting almost the value of A97, but it's missing a sign. So the absolute value, it has no problem getting it correctly, but somehow it's always missing a sign. And I think if you combine these two axes, meaning that if we also count when the model gets just the absolute value correctly, I think this will boost the accuracy to, I think, I forgot the number, but it's around 80%. It's a much larger number. The second experiment we ran was that, well, if the model cannot predict A97 perfectly, can we give it an easier task? So for example, can you predict A97 mod 2 correctly? That should be easier because there are just two values that are possible. And there's nothing so special about 97. So we can also ask that, okay, so give every other prime less than 100 just to predict A2 mod 2 or predict A3 mod 2. And indeed, this is much easier for the model. And the result was that except for when the target prime is 2, 3, and 43, the model achieved accuracy close to 94%. So that's a much nicer result conceptually. I always get asked this question, what's wrong with 43? Because 2 or 3 are small primes. During those times, I always say, I don't know. But now I want to give you a little bit idea of what our investigation is regarding how the model predicts these values, as well as a further discussion of what possible explanation for the results. So for us to explain that what's happening for the model, we have to talk a little bit about the models themselves. For example, the transformer model that we use, that is the standard backbone for language modeling. And in particular, that all the modern day large language models use transformer as an architecture. In our setting, we don't have to go deep into it at all. So the main takeaway from us is that there is a pipeline for a transformer model. So in our case, you take the AP values in the input. These are numerical values. And in particular, these are integer values. And the first thing the model does compared to other models is that essentially what it does is it applies a forgetful functor to it. So all these numbers are now just tokens in the computer science language, but basically is that we forget about the arithmetic structure of them. And then these tokens, without much structure, they will go through a vector embedding lookup. So what specifically means is that suppose we look at a number 1, and the model is supposed to learn a vector representation for that 1. So it's throughout training. And usually the vector representations for these tokens should be large, high dimensional. So in our case, we chose the dimension for the vectors to be 256 to represent simple integers. And these high dimensional vectors representing each tokens for the AP values will go through further processing. So for here, I just put transformer layers and prediction. For the context of this project, we don't need to know any further. So maybe that was a lot, but let's go through an example. So the elliptic curve of conductor 11 has 24 AP values for prime less than 97, -2, -1, 1, and so on and so forth. So in the context of end-to-end, they will become a sequence of 48 tokens. So the reason that we have double the amount of tokens is that in end-to-end, the transform model architecture we use, we separate the signs from the numbers. So -2 will become 2 tokens, which is -2 as well as 2. So now we have 48 tokens without much meanings. And then these tokens will learn a vector representation for each one of them. And essentially, these guys will become a matrix in 48 times 256. If you're interested in further processing part, I have a sketch for our architecture at the bottom. But in the context of our interpretation, this is not so important so far. So the thing we care the most about is how does the model do these things? Especially how does it get a quite decent result? So first, we claim that the model appears to use input values, but not using the input values directly. You take the input values mod 2 to predict A97. So this will also help explain the confusion with the signs. This is what I mean. Recall that each AQ values are now high dimensional vectors. It's hard to visualize them. But however, we can take a PCA projection of these high dimensional vectors and project these vector representations of tokens to 2-dimensional space. So now you see a clear separation by congruence classes mod 4. So if the AQ value is with absolute value, anything 0 mod 4, this is going to be in the red arc at the top. And if the value is 2 mod 4, then it's going to be the blue dots on the lower right. And everything that is odd is going to be on the left-hand side. And the confusion with the sign comes into the fact that you will see that, well, it's really hard for the model to distinguish negative and positive. They're both somewhere in the middle, so they carry essentially no information. And if we're thinking about another explanation with confusion with the sign is that if the model is using AQ mod 2, possibly to predict some information about A97 mod 2, then this kills the distinguishment between the signs. So you will see that if you do the same thing for a model that is not trained to predict A97, but to predict A97 mod 2, for example, or actually any AP mod 2, and you take the vector embeddings again, vector representations for the tokens again, and do the PCA embedding projection again. And then you will see almost the exact same phenomenon, that the model is distinguishing these AP values by their congruence classes mod 4, almost exact same positions as well, these separations. It's a very, very similar phenomenon. The figure below is the PCA projections for the task for predicting A97 mod 2. We would like to say that there are also early signs that the model is not just using information mod 2 and mod 4, but maybe other local informations as well. So with a slightly different architecture, that we also see the PCA projections will also separate according to congruence classes mod 6. So always the plus and minus in gray is going to be in the middle. And here you will see 0 mod 6 in red. And then everything that is 2 mod 6 in green. And then you will see the values that are 4 mod 6. 4 mod 6 is going to be in blue, and 3 mod 6 is going to be light blue, and so on and so forth. So it's a very, very common phenomenon for the model to do this congruence class separations. So at the point when we concluded the paper, my collaborators and I were not very clear of a nice explanation what the model is doing. However, after discussing these results with a number of fellow number theorists, and if you're listening, I thank you for your help. One possible explanation, and it's definitely not certain yet, but it's just a possible explanation, is that the model is exploiting the arithmetic structure in the data by memorizing quadratic twists. So if you look at a quadratic twist of a elliptic curve, then essentially what's happening is that you add a d to y squared. And for many primes that are good reductions for the elliptic curve and the quadratic twist, you will see the AP values is just the plus minus of the original AP values. And indeed, there are many curves in our data set are quadratic twists of one another. So that's a possible explanation just by memorizing these sequences, but missing a sign. So this could explain the confusion with the sign and also the dependency on the information mod 2. But however, even though this is quite interesting, but if the takeaway is that transformer just does things by memorizing, this wouldn't be much interesting. So the question would be, can a transformer model genuinely learn an algorithm rather than relying on memorization? And I would like to propose yes. And I would like to propose an example suggesting the answer is yes. But unfortunately for this example, we have to go to combinatorics. And I have to introduce a new object. The new object of interest of study is dig path. So dig path is semi-length n, monotone lattice path of n by n grid that stays above the diagonal. But perhaps a picture is better than 1,000 words. So you will see here, if the semi-length is 4, then essentially you have a 4 by 4 grid. And all the dig path are going to be pictured below. And there's also an algebraic way to describe these dig paths. So they can be encoded as dig words of length 2n, where up is 1 and right is 0. So in the example for the last path, the dig path is going to be 1, 1, 1, 1, and 0, 0, 0, 0, all the way up and all the way right. Dig paths are very interesting because there's encoded symmetry among them. And before we talk about symmetry, we have to talk about 3 statistics associated with each path. So essentially describe some phenomena geometrically associated with dig path. These 3 are area, bounce, and div. So let's talk about the first statistics, area. So area associated with a path essentially describes the full number of full boxes between the dig path and the diagonal. So in particular, you can have, for a dig path, you can have a area sequence that records from top to bottom the number of full boxes between the path and the diagonal. So for this one, the first entry in the area sequence is 0, and second one is 1, and 2, and 2, and so on and so forth. And the area will just be the sum of all the entries in the area sequence. So it's describing some relationship with the diagonal. Now, the bound statistics is also something that describes relationship with the diagonal. So if you have a dig path that's marked in red, so you can also start shooting a ball from the origin. And when the ball hits the dig path in red, it bounces off to the diagonal. And when it hits the diagonal, it bounces off to the dig path, and so on and so forth. So in this particular example, that the ball bounces off at 3, 6, and 8. And for the bound statistics, you just take the sum of the semi-length n minus the locations of the bounces. So in this case, for this example, it's a minus 3 plus a minus 6 plus a minus 8, which is equal to 7. So bound statistics is also describing some relationship between dig path as well as the diagonal. And the third statistic is a little harder to describe, but by its definition is pairs of rows so that in the area sequence, they're either the same or the previous row is one more than the later row. So for example, the 2, 2, that the first 2, 2 from bottom to up that you see, that will count as a pair. And 2, 1 will also count as a pair, but 0 and 1 wouldn't count as a pair. So the slogan of that will just be, look, the dim statistic will be describing the number of pairs of rows where in the area sequence, they're almost the same. So the asymmetry is as follows. They actually come from the work of algebraic combinatorics, so Hyman and Heikland. We know that there's actually a very unique bijection, which is called a zeta map, on the set of dig path that not only is a bijection, that's not surprising, but it exchanges area and bounds as a pair with dim and area as a pair. So specifically what's happening is that if you think about an input pi, and when it's sent to output zeta pi, then the statistics area and bounds in the input will be equal to the dim of the outputs and area of the output. So let's look at an example. If we have an example where the input sequence is on the left, it goes all the way up and all the way right, and then the unique image under this bijection is going to be up, right, up, right, up, right. So if you think about this, there are really two extremes being exchanged. And if you think about the area statistic for the input, that's going to be maximized because that's every box possible. And the bounce is going to be minimized because the only place where it bounces off is the endpoint on the diagonal. That's for the inputs. So that means that the dim should be also maximized, and area for the output should also be minimized. And that's also what we see, because in the output, the dim describes the pairs of rows that have very similar areas, and every row is exactly the same. So the dim of the output is going to be maximized, and the area of the output is going to be minimized. So the unique symmetry was the point of interest, zeta map. In our machine learning experiments, this is doing work with my wonderful collaborators, Jackson and Lee, we trained transformer models again to learn the zeta map on the for dig words for fixed semi-length n. So if we're describing this as a very concrete task, is that given a dig word, we wanted to predict image under the zeta map. For example, if the semi-length is 5, then the input is a length 10 binary sequence, and the output is going to be a length 10 binary sequence. So it's like a sequence-to-sequence translation. And we actually experimented with many semi-lengths from 11 to 15. We actually also experimented with a variety of transformer architectures. And our main observation is contrary to the learning order example, most models were able to achieve near perfect prediction accuracy. And what's interesting is that among the model we tested, we had the simplest encoder-decoder model, a special architecture for a transformer, which we call minimal Dick transformer. And it has just the simplest setup possible. And despite the model's simplicity, the minimal Dick transformer was able to achieve 100% accuracy. So it's predicting every output very correctly. And this is the model that we're able to get an explicit algorithm out. So we're able to explicitly extract the algorithm implemented by the model internally, which we call the scaffolding algorithm. But before I tell you what the algorithm is and what it looks like, I want to make two remarks. The first remark is that to the best of our knowledge, the scaffolding algorithm is the first algorithm interpretation of the zeta map that does not rely directly on the area sequence. Because zeta map is a well-celebrated map in combinatorics, there are many algorithm interpretation of the zeta map, but all of them will directly rely on the area sequence, but the scaffolding map does not. And when we prove the scaffolding map is actually the zeta map, and the validity of scaffolding map is entirely mathematical. So the machine learning component, which I'll say very briefly in a moment, will only be a discovery aid, and it does not replace the mathematical proof. So the key to the extraction, unfortunately, we'll have to go a little bit deeper into the machine learning component, but is to examine the cross-attention in the transformer model. So from a very high level, after the embedding lookup was said in the very beginning, the zeros and ones will become high-dimensional vector representations for them. And in the case of our Dick path translation, that you have suppose that in the input sequence, you have just 4 tokens, 1, 0, and 1, 0. But these vectors only have 1, 0, 1, 0 information. They don't have the sequence information. They don't have context. So these vectors will go through something called encoder and become the green boxes that encodes not only their zeros and ones, also their neighboring informations as well. And if you on the parallel side, if you remember how ChatGPT and all these chatbot they generate your answers, is that they will generate word by word. So the same thing will apply to our Dick transformer. They generate the output steps one by one. So in this case, the demonstration is that so far we just generated one step, which is 1. Now, the 1 also needs context, especially when we generate more and more words. So they will also become green boxes to carry the information of other tokens as well. So what is this cross-attention thing that we're looking at? Well, the cross-attention thing we're looking at is to describe that when you generate the next step, where in the input sequence matters. So specifically, you take the vectors for ones and zeros in the input, and you take the output vectors, and we compute a dot product. Now, because we just generated one step in the outputs, so now the cross attention is going to be a 1 times 4 matrix. If we have generated 2 and we try to generate a third, the cross attention will be 2 times 4 matrix, and it will become 3 times 4, and so on and so forth. Every row will tell you that when you generate the following step, where in the input sequence matters. So in this demonstration, that's the only input sequence, the only positions in the input sequence that matters is just the zeros in the second and fourth position. And only if the input positions are non-zero in the cross attention, that they will go to the further processing for predictions. If in the cross attention that these positions are mapped to 0, they will not be used at all for prediction. So in our case, this very technical part actually ended up being our major hints of what the model is doing. So if you look at the figure here, I know this is a lot to look at, but if we look at the upper left corner, the blue path is the input path, and the output path is in red. So everything else is just a visualization of the cross attention matrix. So the one on the right, the first cross attention matrix, these columns, will basically say, okay, where in the input sequence, that's when we generate the first step that will matter. And the second is when you generate the second step, and the third with 3 rows is when you generate the third step, and so on and so forth. And this is a lot to look at, and this is quite fun to actually see if there's patterns, and it could be mildly triggering your obsession as well. At least I think that's what happened for me. But one thing that's very easy to see is that first you can see a triangle shape at the very bottom. And moreover, if you stare further, that there are always consistently gaps in these attention matrices. So this means that not only that the model is doing something that is structural, maybe there is hope that we can understand what the model is doing. And another hint is that if we zoom in to the attention pattern during the generation of the first token, and as we said, if we generate the first token, then you're just going to have 1 times 26, because we have the semi-length is 13 here, as a matrix. So you just see a bunch of columns. And the picture on the right, the cross-attention matrix, just has 4 columns. That means that there are only 4 positions in the input that mattered when you generate the first step in the output. And if you try to map where in the input sequence would matter when you generate the first token, I mark these guys in red. So one thing you can notice, not hard, is that these guys are all right steps. But they're not just any right steps, they are corners. They're not just any corners, they're corners that are furthest away from the diagonal. So 2 observations. They're all right steps where the model is paying attention to when generating the first tokens. And they're always going to be the corners furthest away from the diagonal. This was a major hint we were trying to understand what the model was doing. And eventually, from tracking these attention matrices and using other interpretability results, we're able to actually get a concrete algorithm out of it. And we named it the scaffolding algorithm. So the idea is that the algorithm will look like agents moving along the scaffolding to collect information. So if you don't know what a scaffolding is, you'll see a lot of these platforms under constructions, for example, in the great city of the city of New York, like everywhere. So let's see a demonstration what the model actually does. But for now, I think I'll have to stop share and show you via link. All right. So let's take the following as an example. The input sequence is marked in blue. And since the transformer model is always paying attention to the corners, let's always first mark all the corners. And if it starts with the corners that are furthest away from the diagonal, let's mark 1. That's furthest away from the diagonal. And then mark the second one from right to left. That is furthest away from the diagonal. And then there are no more corners that are furthest away from the diagonal of the same distance. Then what we're going to do is that we're going to take these positions in the input sequence and append them from right to left in the output sequence. So we'll start with the rightmost peak, because it's a mountain, because it's a peak, in terms of distance to the diagonal, to the output sequence. And then we'll append the second peak to the output sequence. They're both up steps, so we're just appending 2 up steps in the output sequence. Now, among the peaks, there could be agents jumping off. So for the first peak, one agent jumps off to the scaffolding. And for the second peak, you have one agent jumping off from the second to the scaffolding. Moreover, there could be another type of agent not moving along the scaffolding, a shadow agent that's moving along the ladder, the vertical steps. So this is a ninja here to represent this is a shadow agent that moves, they can only move up and down, contrary to the scaffolding agents moving left to right. And we also are gonna consider all the peaks as well, all the corners. Now there are two corners, one corner here on the right and one corner there on the left. And there's no more corners, no more agents that can be jumped out from the peaks. Then we will append these input steps from right to left to output sequence. So the rightmost peak, we'll mark it as completed and appended to the output sequence. And then next rightmost is going to be an agent. That's going to be a right step, marked it as done, appended to the output sequence. And then agent again, marked it as completed, and then appended to the output sequence. Shadow agent moving up, marked it as completed, append it up in the output sequence. And the last peak, same thing, marked it as completed, appended to the output sequence. And all the agents can keep moving. So the agent on the scaffolding will keep moving right. And you can have one agent jumping off from the peak. And there's another peak where you can have an agent jumping off. There's no more steps. There's no more agents. There's no more corners. Then we can append the agents from right to left. So the one on the right first. So a right step marked as complete. Right step, next agent marked as complete. And then the last the right step marked as complete, appended to the output sequence. So this is a demonstration of the scaffolding algorithm. If you're interested, I can try to show you more examples with an arbitrary sequence. I'm sorry for the change of scenery. Now we have to go back to the slides. Before I talk about further application of these kind of extraction of algorithm in number theory, maybe we should say that, should we be surprised that a transformer model can internally learn and implement such a concrete algorithm? But maybe, in my point of view, that's it's better to ask this question in two parts. First, are there other cases where neural networks can be found to implement recognizable algorithms? And the answer is yes, actually, across number theory, algebra, and also stochastic processes. So I'll give you some examples. The first example is modular arithmetic. This is done in non-DATL. So basically, when a transformer model is trained to predict A congruous cost, B congruous cost, their additional results in map P, then what it does is that you map A and B, these congruous classes, to the unit circle. And do their operations there. So this is basically what we teach in elementary number theory, this clock method. There's analogy in group operations as well. So if you think about MAPI as a cyclic group, then you can also try to train a transformer to learn the operations, group operations, in a non-Abelian group. And in the findings of Chantai et al. Is that they were able to show that a transformer model learned group representations for these non-Abelian groups, for example, S5, and use these group representations, which are naturally vector space objects. So it aligns very well with transformer architecture. They were able to show that this is exactly what a model does, use the group representation to learn group operations. You may be interested is that do this phenomenon only happen if you have no noise in your model? That's not the case. So in a recent work joined with Wang and myself, that we find that a transformer model learned to trained on a state space model also have the same phenomenon. The So if you're unfamiliar with state space model, there are stochastic models where you have observable variables, but observable variables are very noisy. They are really driven by something that's called a latent variable that's less noisy, but you don't really observe the latent variables. So we were able to show that the transformer naturally decomposes into two-stage computation. It first infers the latent variable from the observations, and then you will map the representations that has information of the latent variable to forecast the observations. So this is the same pipeline as a classical filtering and prediction structure, for example, Kalman filter. And the second question is that, do models reliably rediscover known algorithms for these tasks? Fortunately and unfortunately for us, no. So unfortunate part is that these patterns that we can observe can be nearly randomized and hard to interpret. But the good news is that we can also discover variants of familiar algorithms. So in the case of modular arithmetic, not only a transformer can do a clock method, they can also do something called a pizza method. Very similar, but slightly different. We can use our scaffolding algorithm as another example to this as well. So this proposes both a challenge, but also opportunity to discover new algorithms. One last thing that I thought was quite interesting is that we live in the stage of chatbot and large language models. So it turns out that cloud as a large language model, they appear to perform mental arithmetic in an actually rather complicated way. But their explanation, when you're trying to see what they did in the thinking process, they will try to explain things that are familiar to us. That is not internally what they do. Now, if we're interested in exploring further in this area, which I think there's great hope for, is there anything that we should be cautious about when applying transform models to number theoretic data? And yes, transform models were designed to do sequence modeling, and they work especially well if the input sequence actually have meaningful contextual dependencies. So dig path, for example, the dig words that we see, they're naturally can be viewed as a formal language. But a distinctive nature of number theory is that the data can carry local arithmetic information that are rather independent, even though they appear to be a sequence. So example, in the previous learning order factor example, even though the model is given a sequence, -2, 1, 1, so on and so forth, the fact that is that the first one you see actually corresponds to an information mod 3. But the second one you see corresponds to an information mod 5. But the plain sequence representation does not explicitly tell you that. So it's possible, it's certainly possible that transformers can infer the context from the surrounding tokens and informations, but especially if you give a lot of data, it's certainly possible. But this doesn't mean the representation they learned will faithfully capture the underlying mathematical structure. Perhaps it's better to give a even more concrete example on Chinese remainder theorem. So if we consider x as congruent to 1, mod 101, and congruent to 23, mod 103, then if we just give 1 and 23 and ask the transformer model to predict 92 and 93, what x is supposed to be, mod the product of these primes, it's very hard. And even if you add the prime information in the input sequence as well, 1 101, 23 103, this is still difficult. And I claim this is because that 1 and 23 are in different modular contexts, and unless you give a humongous amount of data, it's very hard for the transformer to infer these contexts. And I make this claim because that if you tweak the model for a little bit, if you just tell the model, hey, 1, you should go to one particularly designed embedding lookup because you live in 101, and 23, you should go to a different embedding lookup because you live in the context of the mod 103, this becomes a very easy task for transformers. So I should say that this is a thing that I sort of just did for fun. This is not public yet, but if you're interested, I'm happy to share the GitHub repository. So that being said, maybe in some int to int where it's not, there's a natural interpretation of how do we think about integers as words, maybe poly to poly is a natural thing to try. I'm saying this because that's if you give a base to an integer so that you can think about these integers as words, naturally you encode divisibility information about these integers. And a lot of times we don't want to do that. But poly to poly will be different because that you will be just living in the same MOP context. So maybe this will be a nice analogy to the old saying that function fields are always easier than number fields. That'll be an interesting thing to try. So this is an idea that Thomas Oliver has floated around and I'm currently building the architecture for. So I don't have a lot of time, but I also want to say that apart from algorithm discovery, there's another major goal of AI for constructive mathematics, which is to find sparse examples or counterexamples. Now, currently, there are three major approaches, reinforcement learning, that we're going to go in more details. Like Wagner has done great work for combinatorics, Gukov et al., they've done great work for knot theory, and Shepherd et al. Applied reinforcement learning to AC conjecture, which we'll say in more details. The second way of thinking is using evolutionary search with LLM proposed candidates. So a candidate, so for example, that will be alpha involved, which I know that many of you has experimented on. And the third method is generative modeling combined with local search. So some examples include Chaton et al., pattern boost, and Abertzi et al., flow boost. So they're very similar works. I will, for time's sake, I will briefly I'll briefly discuss a current direction only on RL for constructive methods. And unfortunately, because all my work with my wonderful collaborators are currently under double-blind review, I hope to keep the discussion at a high level. But if you have any questions, please feel free to ask me these questions or reach out. So what is RL for a mathematical search? So the goal is to find mathematical objects with a desired property. So a classical example would be finding high-ranked elliptic curves or some unusual algebraic structures. And a natural viewpoint for this kind of construction, if it's suitable for reinforcement learning, is it's going to be phrased as a sequential decision process. So you will have a state that records the current object under construction. And at each state, you can do an action to modify where you're at, your state. And you can have a reward at each state to measure how promising your current construction is. So it's really a very discrete, step-by-step dynamic programming process. And this is very appealing because in these sparse search examples, we don't really know what a successful example should look like. So this is a lot like playing a game like AlphaGo. Like you just keep playing the game to learn that where should I go to find these examples. So more broadly speaking, that any problem that can be formulated as a sequential decision process is a natural candidate for reinforcement learning. So let's illustrate a workflow with Andrews-Curtis conjecture, which is a long-standing conjecture in combinatorial group theory. So basically, the AC conjecture says that any balanced representation of a trivial group with the same number of generators and the same number of relations can be transformed to the trivial presentations, just using a finite sequence of AC moves. And the AC moves there are just three of them. And if you focus on if the number of generators too, everything is very explicit. You have two generators, X and Y here, and two relations, R1, R2. The AC moves are replace one relator by its inverse, replace a relator by the product of itself and another one. The third one is replace a relator by the conjugation of any word in the generator. So in the previous work of Shepherd et al., that they first applied RL to AC conjecture, and they had great results. In particular, they resolved various potential counter examples in potential two major families of potential counterexamples. In the MS example, in the MS series, and that includes 3 infinite subfamilies actually as well, and length reduction for all but 2 presentations in the AK conjecture. So by length reduction, I mean the sum of the length of the relators. But more importantly for us is that what are the states, actions, and rewards in their work? So the state are just the relators, R1 and R2. So for example, literally just at any point, the R1 and R2 at new construction. The action they use are just the AC move, 3 of them. At each point, for 2 relators, you choose one of 3. And the reward, the positive reward that tells the model where to go, how to find these path of trivializing these presentations, is a combination of length reduction for the relators, as we just said, and a large terminal reward when the state is finally trivial. So everything is quite explicit. This is a great example for reinforcement learning, for finding examples. But there's also major challenges in RL for mathematics. But the problem does not really lie in the RL formalism. They really lie in the design choices. So what I mean by that is action space. Even though that's in the AC conjecture example, the moves are sort of explicitly given to you by these AC moves, but the moves are not rich enough for the RL method to work. The moves have to be rich enough so you can go to your desired object in a finite horizon, so you don't go under infinite number of constructions, but they have to be restricted enough so the model can actually learn. And the second challenge is that this is very particular to a mathematical problem. The reward is so sparse. So if you just give the reward being 1 if the construction is successful, so for example, if you find a high-rank elliptic curve and 0 otherwise, then the model cannot learn anything because there's no learning signal. It's 0 everywhere, nowhere, like in many places. So the reward should be correlating, but genuine to what you desire, but they should also have mathematical progress measuring as well. The third part is more machine learning side of things. The machine learning model, the agent is moving around should be appropriate for the problem. So in a follow-up work that we were able to show that by addressing these particular issues, these 3 issues, we can substantially improve the performance of the earlier baseline of Shepherd and Tell. But what's the implication for number 3 then? As far as I know, there are not a lot of RL applications, reinforcement applications to number theory. And as far as I understand is that the action design is not so clear. So take finding a high-rank elliptic curve, for example. How do you, it's very easy to define the states. It's just going to be the elliptic curve that you're currently constructing, you're looking at. But how do you actually move? Like, do you just tweak one coefficient by 1, or it's not exactly clear. I'm sure there are great examples where we can use reinforcement learning for. And if you have ideas, please let me know. At the very last part, I want to say that through all these explorations, we might be able to find very interesting mathematical observations. Memorations, as discussed in the previous talks, is one of them. I may not repeat. Another thing is rather new. So one observation that we had with my collaborators is that if you write down the minimal Y-stress equation for a elliptic curve, I apologize for writing the coefficients in capital A, I have a reason. Then joined with my collaborators, Banwitz, Lee, Oliver, and Pozniakov, we found that if you look at A1 as a Y-stress coefficient, that's congruent to A2 as the Frobenius trace mod 2. And if you look at A2 in the Y-stress coefficient, that's congruent to A3 as the Frobenius trace at 3 plus 1 minus A1. Now this A1 is the coefficient, mod 3 minus 1. And the capital A's are curve dependent. So for different curves in the same isogeny class, they should be different. But the Frobenius traces are not. And another thing that's interesting about this is that this seems to be true for all the examples that we see, regardless if 2 and 3 are primes of good reductions for E. Because I think if 2 and 3 are good primes for the elliptic curve, then you can just do a brute force enumeration by looking at the mod 2 and 3 Y-stress equation, try to show this is true. So this might be a trivial fact for experts. So if anyone that aware of this fact or think this proof is more or less straightforward, please let us know. But I think this is a quite interesting observation. Well, thank you very much for listening. I know I've said a lot of things and I couldn't get to details for many things. So please feel free to contact me anytime that if you have any questions or if you just would like to chat about any kind of machine learning for number 3, I'll be happy to talk.
Thank you, Coco. Well, this is a great time for some questions. Would anyone like to ask anything? I see one person has their hand raised. Vasily?
Yes, hi Coco. I guess I could just walk down the hallway and we can talk in person, right? So, but yeah. So my question may be quite naive. So, do you understand correctly that I mean, at the foundation of machine learning, that the machine learning algorithms that you use, you still have like all these tuning parameters, biases, whatever they're called, right? So they're kind of we think that they're of continuous nature, right?
Yes.
So we don't think of them as discrete.
No.
So
No.
I'm curious here, are there situations when it's like when they're considered discrete? And then in fact it's interesting if there is a combination when you kind of in the beginning you kind of have this discrete machine learning that kind of prepares your data set in such a way that continuous can do better after this kind of an additional step. So are there situations like this or not?
I think so. So I can answer this question in a number of ways. I do think when we think about language modeling, I do think of them as discrete modeling.
Oh, really?
Yeah, because everything that goes inside of a model is discrete, even though the manipulation is the vector representations in continuous spaces. But everything goes inside is discrete. And another thing is, yes, there are certainly results where you combine various kind of neural nets, which, as you said, there are continuous learnings with more discrete machine learning models. For example, a tree model, decision tree model. Yes, so definitely
A
there are
decision tree, yeah.
results like this. Yeah, I think it depends on which area that we're interested in. I think for scientific discoveries, there are definitely more novel combinations of all sorts of models. Where in language modeling, like it's kind of now it's just transformer. So yes, definitely room for a combination for both.
And can I ask one more question?
Yeah.
Is it okay? Yeah, so I experimented with machine learning for certain setup, and I wasn't successful. And then somebody who is using this in industry, when he looked at this, he told me that why even trying this? There are no patterns. So there are no patterns, so there's nothing to learn. So are there like easy ways to, well, not easy, of course, I mean, one way to see that there are no patterns is to try machine learning and see that it doesn't converge anywhere. Uh, and are there like other tools like compute some invariant or something, compute something like an entropy or something, and that tells you that, okay, so it's likely that there are no patterns, don't try machine learning.
Yeah, I think that's a great question. I think in a lot of times that's when you say convergence, I'm assuming that you're training something that is like a neural net or something.
Yeah, right.
There are a lot of machine learning models, and some will work better than the other ones. So, for example, a tree model will actually work very well in a lot of cases with tabular data. And neural nets are great because they are like universal approximators for continuous functions. So they're very like flexible in that way. But like if you train them for more discrete tasks, as you're saying, that they may not be appropriate. So my line of thoughts will usually just think about if it falls into discrete or continuous. And if it's discrete, try some sort of tree model. And if it's continuous, try some sort of a neural nets or maybe simple linear regression or regression regression. And there are models that are more powerful than the other ones. So for example, transformer is more powerful than like maybe a simple neural net. So after a series of explorations of things work or not, then I will get an idea that's okay. So is there a relationship? Is the relationship deterministic? Is the relationship random? Yeah. So I would say that just from experiments.
Thank you. Yeah, I guess we can continue discussion in person because there's another hand. Yeah,
yes, Crystal.
Hi, thank you so much for the really good talk. I was wondering if there's any or a lot of work where people have used genetic algorithms in particular for machine learning for number theory problems.
Yeah. So generic algorithms, I would say that. So let me go back to here. Can you still see my slides or am I hallucinating?
Yes, we can see them.
So the second point here, the evolutionary search with LLM proposed candidates, we can find paper termed AlphaEvolve. So that's essentially a genetic algorithm. That's basically the LLM will propose an algorithm to find examples and for whatever purpose that you desire. And how it evolves is actually through a genetic algorithm. So you pick the algorithms that give you nice results and then evolve with genetic algorithm.
But it's pretty new. Like there's not like a lot of work that's been done on it.
I think there are a lot of experimentations on AlphaEvolve. So for example, I as I recall, I think Terry Taut had a paper on it. I think that a lot of people are experimenting on AlphaEvolve for number theoretic things. I think they're the most straightforward to apply because like the structure is already there. And I'm sure there's going to be a lot coming out in the near future.
Thank you very much.
Wonderful. Any other questions here? I guess I had a quick one. If you were thinking about working in vector spaces over finite fields, what do you think the capacity is for these models to learn relations among the vectors, like linear relations, quadratic relations? Like, what do you think the limit would be?
I have no idea. So, but what I can answer is a very concrete example. So now I have to go back. Now I have to go back to this modular arithmetic example. So in the modular arithmetic example, because everything in the finite fields, like they're essentially doing things in, I guess, finite groups, but we can try to generalize to finite fields. What is happening is that these congruence classes are being mapped to vector spaces. But if you try to visualize where they are in the vector space, they will fall into a unit circle like very neatly and nicely. So I guess whether the capacity of these models will be able to do, I think it would just depend on how, like it comes down to a very deep question is how much vectors can have powers over whatever things are happening inside of vector fields. But because I do expect this alignment between finite fields and some sort of nice vector space representation. I don't know if this is a nice answer.
Yeah, thank you. Wonderful. Well, let's thank Coco again. And our next talk will be April 14th with Daniel Litt.